Myself, Dr. K. Anita, Assistant Professor, Department of Science and Humanities, Hindustan College of Engineering and Technology, Coimbatore. Through this video, we are going to see vector spaces. Now we are going to see definition of field, definition of vector spaces, and an example of vector spaces. Definition of field. A field is a set F together with two binary operations on F called addition and multiplication. These operations are required to satisfy the following properties referred to as field axioms. Let us take A, B, C are arbitrary elements in F. First, we want to show associativity of addition and multiplication. A plus B plus C equal to A plus B plus C and A dot B dot C equal to A dot B dot C. Next, commutativity of addition and multiplication. A plus B equal to B plus A and A dot B equal to B dot A. Next, additive and multiplicative identity. There exist two different elements 0 and 1 in F such that A plus 0 equal to A and A dot 1 equal to A. Additive inverse. For every A in F, there exists an element in F denoted minus A called the additive inverse of A such that A plus minus A equal to 0. Next, multiplicative inverses. For every A not equal to 0 in F, there exists an element in F denoted by A inverse or 1 by A called the multiplicative inverse of A such that A dot A inverse equal to 1. Next, distributivity of multiplication over addition. A dot B plus C equal to A dot B plus A dot C. Next, we are going to see definition of vector spaces. A vector space is a non-empty set V of objects called vectors on which are defined two operations called addition and scalar multiplication by scalars. Scalars may be real numbers. Subject to 10 axioms listed below. The axiom must hold for all the vectors u, v and w in V and for all scalars c and d belongs to F. U and V belongs to V, then U plus V is also in V. Closure axiom is true. Next, U plus V equal to V plus U. Commutative property is true. Next, associativity under addition, that is U plus V plus V W equal to U plus V plus W. Next, identity, there is a zero vector 0 in V such that U plus 0 equal to U. Next, for each u in V, there is a vector minus u in V such that u plus of minus u equal to 0. So, inverse property is true under addition. Next, the scalar multiple of u by C denoted by Cu which belongs to V. Next, C into u plus V equal to Cu plus Cv. Then, C plus D into u equal to Cu plus Du. The distributive laws are true. Next, C into du equal to Cd into u. Next, 1 into u equal to u. Identity in under multiplication. The above 10 axioms are satisfied. Then we say that V is a vector space. Next example of a vector space. Now we are assuming 2 by 2 matrices A, B, C, D where A, B, C, D belongs to capital R under matrix addition and scalar multiplication is a vector space over R. First we assume M2 of R equal to set of A, B, C, D where A, B, C, D belongs to R. Now we take two matrices A, B which are belongs to M2 of R where A equal to A, B, C, D, then B equal to A1, B1, C1, D1 over R. Now we take A plus B equal to A plus A1, B plus B1, C plus C1, D plus D1 which belongs to M2 of R where A plus A1, B plus B1, C plus C1, D plus D1 belongs to R. Therefore, closure axiom is satisfied. Next, A plus B equal to B plus A. Since a plus a1 equal to a1 plus a, b plus b1 equal to b1 plus b, c plus c1 equal to c1 plus c, d plus d1 equal to d1 plus d. Next, a equal to a1 b1 c1 d1, and we take b equal to a2 b2 c2 d2, then c equal to a3 b3 c3 d3. By using these three matrices, we want to show that associative is true under addition. A plus B plus C equal to A plus B plus C, which is true because AI, BI, CI, DI belongs to R. Next, identity. For any A belongs to M2 of R, and we take 0 matrix 0 equal to 0, 0, 0, 0. Then we add A plus 0 equal to, again we are getting the same matrix A. Then identity exists. Next, if A equal to A, B, C, D belongs to M2 of R, then we take A, minus B, minus C, minus D, that is equal to minus A belongs to M2 of R. Now we are adding A plus of minus A equal to 0, 0, 0, 0. We are getting 0 matrix. So the above 5 conditions are satisfied. Then we say that M2 of R comma plus is an abelian group. Next, if alpha belongs to R and A equal to A, B, C, D belongs to M2 of R, then we take a scalar multiplication alpha A equal to alpha into A, B, C, D equal to alpha A, alpha B, alpha C, alpha D, which is also belongs to M2 of R because alpha A, alpha B, alpha C, alpha D belongs to capital R. Therefore, scalar multiplication is defined. Next, we take a scalar alpha belongs to R and A equal to A, B, C, D and B equal to A1, B1, C1, D1, which are belongs to M2 of R. Now we take alpha into A plus B equal to alpha into A plus A1, B plus B1, C plus C1, D plus D1. Then we are multiplying by scalar. Then we get alpha A plus alpha A1, alpha B plus alpha B1, alpha C plus alpha C1, alpha D plus alpha D1. Next, we take alpha A plus alpha B equal to alpha into the matrix A, B, C, D plus B alpha into A1, B1, C1, D1. That is equal to alpha A plus alpha A1, alpha B plus alpha B1, alpha C plus alpha C1, alpha D plus alpha D1. Then we are getting alpha into A plus B equal to alpha A plus alpha B. Distributive law is true. Next, we are taking two scalars alpha comma beta belongs to R. Then a matrix A equal to A, B, C, D belongs to M2 of R. Then we take alpha plus beta of A equal to alpha plus beta into A, alpha plus beta into B, alpha plus beta into C, alpha plus beta into D. Then we are getting alpha A plus beta A, alpha B plus beta B, alpha C plus beta C, alpha D plus beta D. Now, alpha A plus beta A equal to alpha into the matrix A plus beta into the matrix A. Then we are getting alpha A plus beta A, alpha B plus beta B, alpha C plus beta C, alpha D plus beta D. Then from the above two, we conclude that alpha plus beta into A equal to alpha A plus beta A. For every A belongs to M2 of R and alpha comma beta belongs to R. Next, alpha comma beta be any two scalars which belongs to R. A equal to A, B, C, D belongs to M2 of R. Then alpha into beta A equal to alpha into beta A, beta B, beta C, beta D. Then we are getting alpha beta of A, alpha beta of B, alpha beta of C, alpha beta of D. Then we take scalar outside. Then we are getting alpha beta of A, B, C, D. That means alpha beta of A. Distributive law is true. Next, 1 belongs to R, 1 is any scalar, and A equal to A, B, C, D, which belongs to R, M2 of R. Then we take 1 into A equal to A, B, C, D. Again, we are getting the same matrix A. So, identity is true under multiplication. So, all the above axioms are satisfied. Then B is said to be a vector space. Therefore, M2 of R is a vector space over R. Hence the result. Thank you.